Today we're going to crack the code on two of the most powerful ideas in math and computer science, recursion and induction. Now, I know they sound kind of intimidating, but trust me, they're built on a super simple step-by-step logic that secretly runs our entire digital world. And once you see it, you're going to start noticing it everywhere. So let's start with a puzzle. Let's say you've written some really important code, and you need to prove, really prove, that it works perfectly for every single possible input, all the way up to infinity. How on earth could you possibly guarantee something like that? It sounds impossible, right? Proving something an infinite number of times? Well, it turns out mathematicians have this brilliant and, surprisingly intuitive trick for tackling exactly this kind of challenge. Yeah, obviously you can't just sit there and plug in numbers one by one forever. You'd literally be there for the rest of time. So you need a smarter strategy, a kind of logical guarantee, like an unbreakable chain, that ensures if one case is true, the next one has to be true too. And this is where the real fun begins, because the solution isn't some terrifying, complicated formula. Nope, it's an idea you've probably understood since you were a kid. It is all about dominoes. So the formal name for this logical superpower is mathematical induction. But honestly, it's way easier to just think of it as the domino effect. Because if you can figure out how to knock over an infinite line of dominoes, then you already get the gist of induction. Just think about it for a second. To topple a whole line of dominoes, no matter how long it is, you only need to be sure about two things. First, you gotta physically push over the very first one. That's a must. And second, you have to make sure that the fall of any single domino will, without a doubt, cause the next one in line to fall. If you've got those two rules covered, the entire line is guaranteed to go down. Okay, let's really break this down, because this is the heart of the whole thing. Tipping that first domino? Well, that's what mathematicians call the basis step. All you do is prove your rule works for the very first case, which is usually n equals 1. Simple enough. And making sure the next one falls, that's the inductive step. This is where you prove that this falling action is, well, contagious. You prove that if any random domino k falls, it's absolutely guaranteed to take the next one, k plus 1, down with it. All right, enough with the dominoes for a second. Let's see how this logic actually works to prove a real mathematical formula. Okay, here's our mission. We want to prove that the sum of all the whole numbers from 1 up to some number n is always equal to n times n plus 1 all divided by 2. It's time to set up our dominoes. First up, the basis step. We gotta tip that first domino. So, does our formula work for the simplest possible case when n is just 1? Well, the sum is 1. The formula gives us 1 times 2 divided by 2, which is also 1. Perfect. 1 equals 1. The first domino has officially fallen. Now for the really clever, kind of mind-bending part of the whole process. It's called the inductive hypothesis. Here's the deal. We don't know if the formula works for every number yet, but we're just going to assume it works for one single random domino somewhere in the middle of the line. We'll just call it k. So with that assumption in our back pocket, our only job, our only goal, is to prove that if our formula works for k, it absolutely has to work for the very next number, k plus 1. Logically, the sum up to k plus 1 is just whatever the sum was up to k plus that next number, right? And here it is. This is the key move. This is the whole magic trick of induction. Since we assumed our formula was true for the sum up to k, we can literally just swap it into our equation. We're using our own assumption to build the next link in the chain. It's pretty cool. From here, it's just a little bit of algebra. We find a common denominator, we simplify it, and would you look at that? The final result has the exact same structure as our original formula, just with k plus 1 plugged in instead of n. This proves it. We've shown that if any domino falls, the next one is guaranteed to fall. Our chain reaction of truth is unstoppable. The proof is complete. Okay, so we've seen how induction is an amazing tool for proving that a property is true across an infinite set. But let's pivot for a second. What if we're not trying to prove something is correct, but we're trying to build something complex from the ground up? So yeah, induction is a fantastic detective for verification. But what about creation? How do we actually build things, like the branching folder structure on your computer, or those beautiful, infinitely complex fractals you see in nature? Well, for that, we need induction's creative twin. Meet recursion. It is the art of defining something in terms of a simpler version of itself. And hey, take a look at that structure. It should feel incredibly familiar. Just like induction, it needs a definite starting point, the base case, and a reliable rule to get from one step to the next, the recursive step. So, here's the crucial takeaway. Induction and recursion are two sides of the very same logical coin. Think of it like this. Induction is the detective using that step-by-step logic to prove that a property is true for all cases. And recursion is the architect, using that exact same logic to define and build complex structures from a simple set of rules. All right, let's see this creative power of recursion in action. We're going to build a sequence of numbers, not with some direct formula, but just by defining a starting point and a simple rule for how to keep going. Okay, here are our rules. Our base case, the first term, f of 0, is just 3. Simple. And our recursive step, to get any new term, you take the previous term, multiply it by 2, and then add 3. So let's watch it build itself. To get f of 1, we use f of 0, and we get 9. Now, to get f of 2, we use our new result, f of 1, which gives us 21. And to get f of 3, we use f of 2, and we get 45. You can literally see this chain reaction of creation, where each new step is built directly on the one that came right before it. Okay, let's bring it all home. We've got these two incredibly powerful tools, induction and recursion, and they're both running on the exact same elegant one-step-at-a-time engine. So if there's one thing you remember, make it this. Induction is for proving. It's like checking the dominoes to make sure the whole line will fall. It ensures our programs and our logic are reliable. Recursion, on the other hand, is for defining. It's like building Russian nesting dolls, where each doll contains a smaller version of itself. It builds complex things out of simple, self-referential rules. But at their heart, they both share that beautiful two-part structure. You need a solid starting point, and you need a reliable rule for what comes next. You know, this step-by-step logic, securing your first step and then having a solid rule to take the next one, it's the fundamental engine behind so much of our modern world. It's in everything from how Google crawls the web to how Pixar renders these incredibly complex animations. So the question I want to leave you with is, where in your world could you apply this kind of thinking? How can you break down a seemingly impossible problem into just a starting point and a reliable rule for making progress?